Now students, in this video today we will be studying inverse functions. Now, we have already studied inverse trig functions, but this is a little different. This will be a study of just inverse functions in general, okay? Your heading for today is obviously inverse functions, so please write that down, inverse functions, and the lesson today is 1.5. Be sure and include today's date, inverse functions, lesson 1.5, and be sure and include today's date. Now, let's start off by looking at what an inverse function is, okay? The two equations below are inverses of each other. Please copy these in your notes, okay? I will pause a second for you to do that. Copy this equation down and this equation, and understand these two equations are inverses of each other. Also copy down these table of values, okay? I will pause for just a minute to let you copy these down. Again, these two equations or these two functions are inverses of each other, okay? Copy them down and then copy these table of values down. Now, do you see what inverse functions are? Simply put, they are functions that have opposite domains and ranges. For this function, 0, 1 satisfied it. Over here, 1, 0 satisfies this equation. For this equation, 1, 3 satisfies it. For the inverse, 3, 1. All of the ordered pairs are swapped from this table of values to this table of values, okay? And that's what inverse functions are. Simply put, okay? Their domains and ranges have been swapped. They are opposite. So, with that last thought in mind, here are 4 ordered pairs from function h. Okay, now listen to me, students. We do not know. Go ahead and copy these ordered pairs down, please. We do not know what function h is, and that's the whole idea of this problem. Okay, so I'm telling you, here are 4 ordered pairs that satisfy function h. I want you to find 4 ordered pairs for the inverse of h. And by the way, you may as well go ahead and now get used to this symbolism. So make note of this. If I have function h, the inverse of h is denoted like this. H to the negative 1. And you don't say h to the negative 1. That's not proper. You say the inverse of h, or h inverse. So if one function is h, and you see this, you don't say h to the negative 1, you say the inverse of h, or h inverse, okay? So get used to that notation. So with that in mind, since these ordered pairs are from the function h, I would like you to list out 4 ordered pairs from h inverse, okay? So here they are. Think it's so easy, guys. If negative 8, 5 satisfied h, then 5, negative 8 would satisfy h inverse. If 4, negative 2 satisfied h, then negative 2, 4 would satisfy the inverse of h. If negative 7, 1 satisfied h, then 1, negative 7 would satisfy the inverse. And if 3.8, 6.2 satisfied h, then 6.2. 3.8 would satisfy the inverse of h. Do you see this? Really pretty simple, not difficult at all, but I want you to understand what inverse functions are. Now let's take this a step further, okay? What if I gave you an equation? Could you find the inverse of that function? Let's give it a shot. Here are the steps you need to use. Please copy these down. Number 1, substitute x for all of the y's, and substitute y for all the x's. Now let's pause and think about that. Doesn't that make sense? I mean, we already said that true inverse functions have their domains and ranges swapped, and of course domain refers to your x's and range refers to your y's. So doesn't it make sense that if you're given an equation and you want to find find its inverse. Everywhere there's an x, you put y's, and everywhere there's a y, you put x's. Makes total sense. And then step 2 is you simply solve the equation for y. Okay, that's it. 2 steps, and you can very easily write inverse functions. Okay, so let's go ahead and take a look at this. Here we go. I'd like you to copy these 2 equations down if you would, and I want you to write the inverse function for both of these equations. Okay, so let's start with this one here. You can work ahead or you can watch me. That's totally up to you. But if you choose to work ahead, please make sure you're doing it correctly. Okay, find the inverse of this function. Alright, so where the y is, I'm going to put an x. And where the x's are, I'm going to put a y. Okay, there we go. Now, the next thing we're going to do is get y by itself. Now, in this problem here, and I've given this problem to you for a reason, in this problem here, it's going to be difficult to get y by itself. So let me pause and say this. Do understand one thing, students, and please, please don't miss this. As soon as you put x's in for all the y's, and as soon as you put y's in for all the x's, you could technically stop right there and you're done. This equation here is the inverse of this equation here. However, properly speaking, you are supposed to get y by itself. However, in some equations, it will be difficult. Understand that. So in this equation here, I can come over here and I can factor out a y. And I'm left with this right here. But it's still difficult to get y by itself. Now I suppose you could divide both sides by y minus 5 like this. But that's still really not getting y by itself because there's still a y over here. So there will be some problems like this occasionally. And when that happens, you're welcome to leave it like this, okay? But most of the time that won't happen, okay? Now, let's come over here. So this equation here and this equation here, these 2 equations are inverses of each other. Now, let's come over here and let's find the inverse of this equation here. Everywhere there's a y, I'm going to put an x. And everywhere there's an x, I'm going to put a y. That's step 1. Step 2, solve for y. Now, over here that was not really possible to do without a lot of work. But over here it's pretty simple. We're going to get y by itself. So we're going to bring the positive 8 over, or bring the negative 8 over, and make it positive. Next, we're going to divide by 5 to get y by itself. So there's really a 1 right here, don't forget that. So we have 1/5 x plus 8/5 equals y. Now I'd like to show you something you need to see, students. If we're going to call this equation y, we're going to call this equation here y inverse. Okay? So basically what you're saying is this equation here is the inverse of this equation here. Alright, so I hope this makes sense. Again, not at all a difficult thing to do, but make sure you understand how to do this. Replace the x's with y's, replace the y's with x's, and then solve for y. Okay? Now, I want to throw kind of a crazy comment at you, and then show you what I mean, okay? And I would like you to write this comment in your notes, if you would please, okay? So copy this down. Every equation has an inverse function, okay? But not every function has an inverse function, okay? Copy that down if you would, please. Every equation has an inverse equation, but not every function has an inverse function, okay? And I'm going to show you what that means in just a second, but go ahead and copy that sentence down. It's very important you understand this. Every equation has an inverse equation, but not every function has an inverse function. Alright, now let me give you an example below, and you take notes on this however you feel like you need to, okay? Alright, now, here's a coordinate plane. Get a little space here to work with. Now, just kind of sit back and listen and take notes as you feel necessary. This is an equation. Got it? This would be a function. Now, say something, before you say, Mr. Earhart, this is a function over here too. I understand that, but it's written as an equation. It's not written in function notation. Now, if you want to call this a function, I have no problem with that, okay? But the point I'm trying to make is this. If I give you an equation, every equation has an inverse equation, okay? Let me show you. If I were to graph this, here's what I would get. Okay, got it? Now, if I were to graph the inverse of this, alright, it would look like this. Actually, I'm going to change over to a different color. The inverse would look, and again, I'm just sketching this roughly, okay? These are not perfect by any stretch of the imagination. Now, students, would you please listen to me? This red graph here is the graph of this. If I were to find the inverse of this, put an x here, put a y here, and then take the square root of both sides, I would get this graph right here, okay? Now, notice that this green graph is not a function. Let me say that again. Notice this green graph is not a function. It's not, Mr. Earhart, no. Vertical line test. That's not a very good vertical line, but you get the point. If there's anywhere you can draw a vertical line on this green graph in such a way that it intersects the green graph more than once, then it's not a function, okay? So, what I'm trying to show you is this. And I hope I'm explaining this well. You're welcome to say that every equation has an inverse equation. That's fine. I have no problem with that. But if you want to get picky and start talking about functions, remember, some functions do not have an inverse function. And here's an example right here. This is an example. Look, if I were to graph this right here, it's the same thing as this over here. I would get this red graph. If I were to find the inverse of this, pretend there's a y here and put an x. Pretend there's an x here and put a y. Take the square root of both sides. And then for y right here, get rid of the y and put this. F inverse of x. So here's my f of x function, and this is my inverse function. Well, it's not a function. Look, when you go to graph this right here, look, it's not a function. So not every function, students, has an inverse function, okay? I mean, sure, here's the equation, but let me ask you a question. Let me ask you a question. Is this equation that I just circled here a function? No, it's not, because look at the graph of it, and also every input that I put in is giving me out two outputs. So no, it's not. Now, if you want to talk about equations, hey, all equations have inverse equations because we don't care about the vertical line test if it's just an equation. But when you're dealing with functions, not every function has an inverse function. And here's an example right here. This function here does not have an inverse function because when you find the inverse, then you realize it doesn't exist because this right here is not a what? It's not a function. Okay? So not every function has an inverse function because sometimes when you find the inverse function, or at least you think you found it, it ends up not being a function at all. Please understand that. Now, when a function does have an inverse function, we say the function is 1-to-1. Please make note of that in your notes. Okay? When a function does have an inverse function, when a function does have an inverse function, we say that the function is 1-to-1. Okay? So, understand that. So if a function has an inverse function, we say that the function is 1-to-1. Alright, now continuing on. There is a way to use a horizontal line to see if a graphed function has an inverse function, and it's called the horizontal line test. Okay? So please listen to me very carefully, and I'm not bragging, but I will explain this well. I'm going to write it right here for you, okay? Take really good notes. The vertical line test, we learned that earlier, is for what? Do you remember? A vertical line test shows you if a graph is function. It's that simple. Okay? And we just use the vertical line test right here. I drew some vertical lines and I showed you this green graph was not a function. Okay? So that's what the vertical line test does. Now what does the horizontal line test do for you? Okay, sorry students, I had to pause the video. Okay, I'm not sure exactly where it was, but what does a horizontal line test do for you? Well, let me show you. I'm writing this down, guys, so you don't get confused. Okay? So a vertical line test shows you if a graph is a function. A horizontal line test shows you if a graph has an inverse function. Okay? Now really, that's pretty simple. That's not hard to understand. Okay? The vertical line test looks at a graph and says, yes, it's a function. The horizontal line test looks at a graph and says, yes or no, this graph has an inverse function. It shows you. Okay? So, let's practice this. You can watch or take notes. Let's say I've got a graph, a line like this. Okay? A graph like this. There, a slanted line, okay? Let's first of all decide, is this black line a function? Well, to know if it's a function, use the vertical line test. Is there anywhere you can draw a vertical line that intersects the black graph in more than one place? No. So the vertical line test shows you that it is a function. Now, let's run the horizontal line test to see if this graph has an inverse function. Is there anywhere that you can draw a horizontal line that intersects the black graph more than once? No. So then yes, this graph does have an inverse function. It does. It's that simple, students. Let's try another one, okay? Let's try one like this. Let's get a graph up here of a polynomial function there. Now, my first question for you is this graph a function? Well, if I want to know if this graph is a function, would I use the horizontal line test or the vertical line test? Well, obviously it's going to be the vertical line test because the vertical line test tells you if a graph is a function. So is there anywhere that you can draw a vertical line that intersects this red graph in more than one place? No. Now I know it looks like the graph starts to straighten out and become a straight line here and here, but it really doesn't. It's slowly getting wider to the left and slowly getting wider to the right. So is this red graph a function? Yes, it is. Now, I have a question for you. Is this graph, or does this graph have an inverse function? Does this graph have an inverse function? Well, let's start drawing some horizontal lines. Is there any horizontal line you can draw that intersects the red graph in more than one place? Well, of course, there's quite a few. And some of these green lines some of these horizontal lines are intersecting the graph in 3 places, okay? So, does this red graph have an inverse function? No, because the horizontal line test failed. Now guys, I know I'm not the best teacher around, but I hope this makes sense. Okay? Understand the difference. Okay? Take good notes on this. Vertical line test tells you if the graph is a function. The horizontal line test tells you if the graph has an inverse function. Alright, now let's continue on. Let's move on now to writing the inverse of a graph. And really, students, it should be pretty simple. I mean, look at it. All you got to do is just flip the ordered pairs. Okay? Take a second, please, and copy this down, would you? Copy this down. Put a point at -6, 3, -6, -3. Put a point at -4, 2. Put a point at 1, 3, and a point at 2, 5. I'll pause a second while you do that, okay? And then go ahead and draw a graph that looks very similar to this graph here, okay? Go ahead and do that, please. Okay, students, go ahead and continue to copy this down if you're not finished. I'm going to go ahead and start working on this problem. I want you to write the inverse of this graph. Well, guys, think about it. If -6, -3 exists, then negative 3, negative 6 exists right here. Negative 3, negative 6 right here. Now, if negative 4, 2 exists, then 2, negative 4 exists. Guys, I'm just flopping the ordered pair. That's all that I'm doing. Do you see this? Okay, that's it. It's not difficult, okay? If you've noticed in this class, guys, well, I'll get to that in a second, but so I flip this ordered pair, negative 3, negative 6. Here, 2, negative 4. Now, flop these and we get 5, positive 2 right here. And then flop this point, 1, 3, would be 3, 1 right here. Now, look at what I want to show you guys. See this point here? Okay, first of all, look at this black dotted line. You're probably wondering what it's there for. And I'm going to tell you now why it's there. I want to show you something else about inverse functions. Okay, this black line is the line called y equals x. Okay, y equals x. Now, if you'll think about it for a second. Excuse me. Notice, students, this point here, if you draw a perpendicular line to y equals x, and I know my point's not perfect, it should be about right here actually is where it should be, but notice this, then also draw, I know my line's not perfect, you get the idea. This point here, the distance from here to here is the same as here to here. Okay, if I draw a line from here to here, and make sure it's perpendicular, and then go the exact same amount of distance over here. Again, my drawings aren't perfect, but you get the idea. That point's going to be there, okay? Now, same thing here. Draw a perpendicular line, and it's going to be the same distance over here. Same thing. So that's why they have this y equals x line drawn, okay? And understand that that's always true for every point that exists on this graph, okay? That you can draw a line from the point to y equals x perpendicular, and it'll be the same distance from y equals x to the other inverse point. So what I've done is I have now taken these 4 points and I have written the inverse points over here. Now I'm ready to sketch the graph. So the inverse would look like this. There it is. There it is. Notice it's a reflection in y equals x. Okay? Notice that the inverse function of a given graph, the inverse graph of a given graph is a reflection in the line y equals x. Okay? There it is. Okay, let's go ahead and continue on. Now, there is a way to prove that two functions are inverses of each other. Okay? There is a way to do that. This method involves composition of functions, okay? So there is a way to prove that two functions are inverses of each other. Here's how it works. I would encourage you to copy this down. When you are given two equations, you find the you find the composition going both ways. Now I'll explain what that means in just a second, okay? If you get out x for both compositions, then the two equations are inverses of each other, okay? Let me read this again, and you copy this down. When you are given two equations, find the composition going both ways. If you get out x for both compositions, then the two equations are inverses of each other. Now notice I said you have to get out x, not negative x, not x squared, not x over 2, x. You have to get out x. Let me give you an example and show you what I mean, okay? I'm telling you now that these two functions here are inverses of each other, okay? So, I want you to prove it, though, using composition, okay? So, remember what it says up here. You're going to find the composition both ways. So, we're going to do composition 2 times. We're first of all going to find this composition. F of g of x. And then when I say both ways, then you're going to come over here and find the composition composition g of f of x. You must do both, and you must get out x for both of them. Okay, let's start with this one here. Okay, I'm telling you, these are both inverses, so prove it. Okay, alright, f is my outside function, so I'm going to write 5x plus 8. Then where the x is, I'm going to put a really big parentheses. Now, my next function is g, so I pick up g and I put it in here. Okay, now let's simplify and see if we get x, okay? First of all, the 5 is over 1, so 5 over 1 times x minus 8 over 5. Your 5's would cancel. 1 times x minus 8 is x minus 8 over 1, so you really have x minus 8 plus 8. Your 8's cancel, and you're left with x. Look at that. So far, so good. But remember, it has to work in both directions, okay? So, now let's go ahead and find g of f of x. So my outside function is g. So I'm going to take my g function. And where there's an x, I'm going to put a pretty big parentheses, okay? Now, I'm going to pick up, my next function is f on the inside. So I pick up f and I put it right here. So here's what I have. In my numerator, I have 5x plus 8 minus 8. Well, my 8's are going to cancel, leaving me with 5x over what? 5. Now look what happens to your x, your 5's. They cancel, leaving you with just what? X. Okay? So there we go. So I just proved to you that these two functions here are truly inverses of each other by using this method here. Now students, in closing, there's one more thing I would like to show you, and then we'll be finished with the video today. Let me go back a couple pages here. Hold on one second here. Okay, right here. Remember how I showed you how to decide if a graph had an inverse function. And of course, a horizontal line test shows you whether or not a graph has an inverse function. But one thing we haven't talked about yet is how do we know if an equation has an inverse function, or if a function has an inverse function, okay, without the graph. Now, it's really quite simple, and I want to go back and show you. Remember how the vertical line test or the horizontal line test, they were complete opposites of each other, okay? To see if we had a function, we used the vertical line test. To see if a graph had an inverse, we used the horizontal line test. Well, it's going to be the same thing, folks, okay? Let me show you this right here. Pretend we have this equation right here. Copy this down, please. Now, if I said to you, is this function, or is this equation a function of y? Y is a function of x, okay? Well, we know by now f of x is the same thing as y. You get y by itself, and then you say to yourself, does each input have exactly one output? And the answer would be yes. I don't care what x value you put in for x, you're only going to get out one y value, okay? Now, here's the catch. It's going to be the opposite, just like the vertical line test and the horizontal line test were opposites. If I ask you, now notice I'm not asking you, is this equation a function? I'm asking you, does this equation have an inverse function? Okay, here's what you do. You're used to getting y by itself and seeing if each input has an output. Well, you do it backwards. You get x by itself, and you see if each output has an input. Let me show you what I mean. Let's get x by itself, okay? We're going to take the fourth root of both sides. If we take the fourth root of this side, we have to put plus minus, okay? If I take the fourth root of the right side, I'm left with x. So now, instead of putting numbers in for my input and getting an output, we're going to put numbers in for y, which is usually my output. And and see if I have one input coming out. That sounds a little confusing, but I think you get the idea. Everything's opposite. Instead of getting y by itself, you get x by itself. And instead of putting values in for x, you put values in for y. So think about it. If I put a value in for y, would I get out? Would I get out more than one value? Yes, I would, because I have a plus minus here. Do you see what I'm saying? Let me get a drink here real quick. Guys, I hope that makes sense. Look, if you put in 16 right here for y, well, the fourth root of 16 is 2, but it's also negative 2. So you put 16 in, and you got out 2, and you got out negative 2. Now, I know you're saying, Mr. Earhart, why is not input? Everything's backwards, guys. When you're seeing if an equation has an inverse function, then instead of getting y by itself, you get x by itself, and then you put values in for y, and see if you get two numbers coming out. And now we can say, yes, we are getting two numbers out. So this equation right here does not have an inverse function. It doesn't, okay? So I'm going to sum this up and I'm finally done, okay? If I ask you to test whether an equation is y as a function of x, we learned this earlier this week or last week, whatever, okay? It's simple. You get y by itself. You get y by itself. And you check to see if your inputs have more than one output. But if I ask you, does an equation have an inverse function? Does an equation have an inverse function? Then you get x by itself. Okay? And then you see if your y values give you out more than one x value. And if they do, then no, you do not have an inverse function. Okay? Alright, I hope this video has been a help today. If you have any questions, don't hesitate to call or email.